name is Mark Miodovnik. I'm a material scientist from King's College London. And today we're going to talk about big stuff. I mean, look at this stuff. Look at this bolt. I mean, who could need a bolt that big? And this stuff here, we're going to talk about skyscrapers, mountains and planets, huge things. And we're going to see that matter behaves on the big scale every bit as strangely as it does on the micro tiny scales. And in the previous lectures, we talked really about how different forces dominate at different scales. And at the big scale, the force that we're going to need to worry about, the one that's going to dominate everything, is gravity. It's our invisible enemy. So, how do we beat it? How do we make big things? Well, this is a big thing. This is a mountain. And it's huge. Look at it. Absolutely huge. Or is it? I mean, it all depends on the size and scale in which you look at it. If I zoom out now I'm the size of a planet, and I look down, well, mountains are not so big anymore. And when things are big, it changes everything. You suddenly realize that all the rules are off. And matter behaves in a totally different way. And I want to just get you used to that idea, because I'm going to need you to turn off your common sense in order to understand that kind of thing. And, you know, your common sense is really going to interfere. So first of all, let's just get a feel for how gravity can affect big things. So, I've got a material here, and it's a liquid. So who believes me that this is a liquid? Okay, so you've still got your common sense turned on. All right, I'll try and turn it off for you. Okay, so obviously liquids don't do this. Usually, do they? So this feels very much like a solid. But I hope to prove to you, as the lecture goes on, that this is a liquid. I'm just going to leave it there for the moment. You keep an eye on this stuff as the lecture goes on. We'll come back to that. Here's another bonkers mad liquid. And this is one of my favourite liquids of all time. Mercury. Gosh, who loves mercury? It's just the strangest stuff, isn't it? Now this, what's so strange about mercury is it's a metal, but it's also a liquid at room temperature. Mercury's a heavy liquid. What does that mean, heavy? Well, I'll illustrate what I mean by heavy. This is a cannonball, and that is definitely heavy. And gravity, this invisible force, pulled it down. Do you see that? You're pretty used to that, aren't you? Okay, let's see. Heavy cannonball meet heavy liquid. Okay, we'll take that off. And what's going to happen here, eh? Is it just going to go right to the bottom? Wow. That's incredible, isn't it? A floating cannonball. Let's hear it for the cannonball. Okay. All right, so that's heavy things where gravity is really playing a massive force. Now I'm going to show you material that goes completely opposite direction. I have here the lightest solid in the world. It's so light, you can't hardly see it. Can you see that? Now this stuff is called aerogel, and it's 99.8% air. So it's only 0.2% solid. In fact, you can hardly see where it ends and the air begins, because there's only 0.2 difference, isn't there? And it's got this blue tinge, have you noticed that? Now that's because it's a foam, it's a glass foam, and the holes in that glass foam are so small that they scatter light in the same way that light is scattered in the sky. So while you'll sing it's blue for the same reason the sky is blue. There's no pigment in there. So this is as close as you're ever going to get to holding a piece of sky in your hand, right? It's almost completely sky. And you think, well, God, that's incredible, 99% air. What could anyone possibly want with a material like that? Well, it turns out that NASA used this to collect space dust. It's absolutely amazing, isn't it? So, yeah, I think you have to give a big round of applause for aerogel, the lightest solid in the world. How are we doing with our common sense? It's looking less like a solid now, isn't it? So let's see how big we can build. This is the Burj Khalifa, and it's the tallest building in the world. It's 0.8 of a kilometre high. So that's half a mile high. Of course, I look quite big next to it, don't I? Look like a giant. But actually, if you shrunk me down, this is what I would look like. It's really high! It's absolutely a magnificent building. But, well, what happens if I'm the size of Everest? Now, here I am. I'm a giant. And here if I was to look at the Burj Khalifa now, that's how high it would be. It's down here. Tiny. So, why can't we build anything bigger? That seems pathetic. You know, we've gone to the moon, and yet that's all we're building. Well, we've got a model here of the Earth. Here's England, here's where we are. And if we were to put on a scale the Burj Khalifa, you wouldn't be able to see it. We'd have to have a microscope to see it. So it's down there somewhere, but we haven't seen it. And if you put the mountains on here, again, as you saw with the pictures of the Earth, they're tiny. So this Earth, you can see, has this incredible round sphericals. It's all very, very, very smooth. And that's because the Earth exerts an enormous gravitational field. It's huge. This enormous mass is exerting a force on you, me, that cannonball. How far do we have to go to get out of its hole? Well, I'll show you. I'm just going to say, if we were to build a building this high, not quite this high actually, a bit higher, and 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 a bit higher. If we would build a building, and this is the scale, we built a building 36,000 kilometres high, we'd be what's called a geostationary orbit. So satellites up there, sort of communication satellites up there, they stay in a fixed position with regard to the Earth as they satellite around, and they're not sucked back into Earth. So if we can get up there, 36,000 kilometres away from the Earth, then we can escape the Earth's gravitational field, this tyranny of gravity. So why haven't we done that? Why haven't we managed to do anything close to that yet? So I'm going to need a few volunteers from the audience to help me. Okay, so we've got one there, a lady there, and let's get a guy. Yeah, go on. And one more, yes. So why don't you come down? Yes, all right. We're going to have a competition now, and there will be prizes. And the competition is to escape the Earth's gravity. Okay? So, and what I'm going to try and do is, obviously, you're going to have to try and jettison us off into space now. And if you make it as far as the roof, we will open it for you. So don't worry about that. Don't limit your ambitions. Are you ready? Okay, we'll do a countdown, everybody. 3, 2, 1, go! Whoa, we did it twice! Whoa, I don't know, we'll have to consult the referee, and then letting that go, alright. But let's have a look at the action replay. Okay, and up they go. Oh, it's the old back lips, and I think that got it for you. Well done. Technique! Okay. Now, that was really sporting of them, but it wasn't very impressive, was it, really? Because, I mean, half a second is all we could... And basically, they're no better or worse than most of us, aren't they? So gravity is this incredible tyranny on our lives. It's constantly gluing us to the floor, and that seems really annoying to me. So I started thinking, well, let's try and work out how to levitate. So here we go. Thought, should be able to make a levitation machine. Got in touch with some material scientists who had some ideas about this, and they gave us some of this material, which is called a superconductor. And when you cool superconductors down with liquid nitrogen, so we're going to get down to minus 193 degrees centigrade, then these superconductors, they repel magnetic fields. So the idea is this: gravity pulls magnet down, and we repel the magnetic field with the superconductor, and they equal each other, and we get the magnet to levitate. All right, let's see if it works, though. Is it working? Oh, ho, ho, ho! Okay. Yes. Now, I know what you're all thinking. You're thinking it's a tiny little thread, aren't you? I know. So look, just to prove to you that there isn't anything underneath or over the top. Nothing over the top. And... oh, yes. The thing about that was you had a magnetic field opposing the gravitational field exactly. Turns out that as the magnet gets bigger and bigger and bigger, that gets harder and harder to do. So I thought, well, I'll invent a levitation device that can levitate me. So off I went to my garden shed, and I came up with a levitation device, and this is the world premiere of this device. And I think you're all going to be very impressed, because this really could be the future of us getting off this planet. Do you want to see it? Yes. You don't sound that interested. Come on, do you want to see it? Yes. Okay. Well, I know, you're clapping, but I know you're not that impressed. But just bear with me on this one. This is a levitation device. Look, I'm on the floor, I'm stuck to the floor, now I'm not. Right? I mean, before we had a magnetic field repelling my gravitational force, but now, inside this piece of wood, as we call it, in the technical, there is an elastic force field, which is exactly matching my gravitational field. So, there's an elastic force field in there. At the atomic scale, the atoms are being pulled apart exactly to match my gravitational force. So this is fantastic. Here I am, and it's not just happening to me, it's happening to all you now, right? Because all of you are sitting down, and your gravity is still acting on you. Gravity is not this force that just switches on when you're falling. It's acting on you now, and it's pushing you down to the ground. And if there wasn't an elastic force field underneath your bum now, let's all just think about our bums. No, not too much. That's enough. So it's that elastic force field underneath your bum. So it's the cushion, and then it's the floor, isn't it? So if you think about it, the floor in here, in this whole auditorium, is having to put up with quite a lot. Because before you lot came in here, there wasn't an elastic force field, and now there is a massive elastic force field in here holding you all up. So that's great, isn't it? I mean, buildings just do that for free. Or do they? Let's get a feeling for how much elastic force field they're having to put up with now, in this room. Okay, so how do I do that? Anyone got any ideas how to calculate the total gravitational force acting down now? Anyone? You got an idea? A force meter, yes. And what do we call force meters? In the parlance, in the bathroom perhaps? Anyone? Yes? A scales! You're good. Okay. So it's a scale, isn't it? Well, if we're going to measure this audience, we need a scale that will weigh you all, don't we? So let's get in a big scale. What we thought we could do is kind of get you all to sit on this scale. We borrowed these from Shrek. And he has them in his bathroom, and he let us lend them. He's on a diet at the moment. He's obsessed with his weight. What we want to do is try and measure the audience, how much gravitational force from the audience. So I need some help with this. And what I'm going to try and do is I'm trying to weigh as many of you as I can. But first I'm going to start with one. Now, can I get someone in the front row who's brave enough? Are you brave enough to come and how do you feel about your weight? Are you sensitive about it? No, you're not. Okay, brilliant. Okay. Sorry, what's your name?
Tomasz.
Tomasz.
Yes.
Okay, brilliant. Okay. So, Tomasz, I'm just going to zero the scales. All right, off you get, Tomasz. Now, so let's see, how much do you weigh? 41 kilos. Is that about right?
Yeah.
Good. All right, now, let's see if we can get some more on. Can we get two more of you on there? Is that possible? You two up for that? All right. Come on, then. And so you two get on there and just budge you up a bit, if you don't mind. All right. Now, how are we doing? 128 kilos. All right. Do you think we can get some more? Do you think you three will be able to get on there? All right. How are we doing? 309 kilos. What about you two? You're going to make it on there. You can get on the sort of edge bits as well. What about you guys? Yes? You're up for it? All right. So you four. Let's see if we can get four more of you on. Now, there's there is a game called Sardines that's very similar to this. Oh, this is good. This is good. We're up to 600 kilos. Can we get any more? Come on, let's get the whole of this row on if we can. Is that possible? How are you guys feeling? Are you all right? Is there room?
No.
Come on. All right, now there's a bit of space over here. You came up with this idea, so you should be at the front. Okay, brilliant. Can you get into that little corner there? That's possible? You all get to know each other. This is all very friendly. Oh no! Is there not enough room for you guys at the back? Is there a little room there? Okay, hold on guys, just 2 seconds. So we've got 700, we're on 771, no 80, well let's say 775 kilos. For how many kids? Oh, I didn't count. Did anyone count? All right, let's get off, guys. Brilliant. Thank you. Big round of applause. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 kids, I think. So that turns out to be, has anyone done that calculation in their head? Average weight of kid? 48 kilos? 48 kilos per kid. So that's, let's say 50. And there are about 400 of you here. So that means, a bit of mental calculation going on in my head now, 20 tons. So you weigh 20 tons. That's pretty amazing, isn't it? So before you came in here, this poor building was minding its own business, right? Just having a lovely Saturday afternoon, having a bit of a rest. Then it had to put up with 20 tons of you, and it's holding you up like this, and we never really asked it. So it's produced an elastic force field of 20 tons, just like that. And next time you go out and buy a really heavy, big, new flat-screen TV, think about the building, right? Because the poor old building never got asked if he wanted a big flat-screen TV that weighs half a ton, and it has to put up with holding it even when you're asleep. And those of us in the Society for Protection to Cruelty to Buildings are quite concerned about this accruement of very heavy technology in the home. Okay, so it turns out the buildings are quite good at coping with this, so why can't we just build ourselves off the planet? I'm going to need a couple of volunteers who have ambitions to work in engineering. And the hands are still up. Fantastic. I love that. Okay. Let's have you, sir, there. Yes, brilliant. And madam there. Yeah, brilliant. Okay. All right. What's your name? Charlotte. Your name? Innes and Charlotte. Fantastic. Okay. Now in this game, you do all the work and I get to talk. Is that all right? Anyway, so what I want to do, we're going to try and build ourselves off the planet, well at least the first few steps. And here they are. So we've got the first step. This is my anti-gravity machine, which we now agree is genius. And if you could just add, can you grab some of those and add the next step? That's what we want to do. I basically want to get the idea of building us off the planet. So you put 2 on there. Fantastic. Okay, and then I think if we can get a slat across, yes, that'd be brilliant. I'll put that on. Yes, I see. I do the easy bit. Hooray! I'm up one further bit away from the planet. It's like an enormous game of Jenga, although I hope it won't end the same way. Look, guys, look, you've done a fantastic job. But here we go. Up I go. And we could just keep going, couldn't we? If you were not getting tired and had infinite energy and we had infinite materials. That seems reasonable. Well, thanks very much for helping with that, guys. Really appreciate that. What is stopping us just keeping on going? Well, there is a problem. There is a problem. And in order to tell you about that problem, I'm going to invite some friends to help me work it out.
F-O-R-C-E, let's learn about gravity. F-O-R-C-E, let's learn about gravity. F-O-R-C-E, let's learn about gravity. 5, 6, 7, 8.
Okay, well done, fantastic guys. Now, who was at the top? Who was at the top? What's your name? Kira. Kira, you're at the top. Now, how was it at the top? Did you feel an enormous force on your shoulders? No. Did you feel yourself pressing down on other people? Yes, you did. And how was it at the bottom? You guys were all at the bottom. I was at the bottom. Do you guys take it in turns? What goes on?
We've got all the way.
But it is. Basically, this is the problem, isn't it? Is that as you build things higher and higher and higher, you guys are always going to have to take all the weight that goes above you, aren't you? And that just gets worse and worse and worse. So we put another tier on top, which we're about to do, aren't we? Oh no, I'm just joking you. Just joking you. Okay. Actually, but we'll just run that through again because we just want to get the hang of it. And I want everyone to look at these guys' faces on the bottom, not the top. She gets all the glory all the time. Look at the people doing the work at the bottom. Okay, let's go for it again, guys. Let's hear it for these guys. Okay, so what we saw there really is this sort of, if buildings had emotions, right? All the bricks and stones at the bottom would be going, oh, for all the time, wouldn't they? Because they've got to hold the whole building up. And as the building gets higher and higher and higher, their load doesn't get any better. They have to take more and more and more weight. So gravity is constantly working, even in static structures like this. And what we have to do is find the materials that can cope with that kind of pressure. Okay. So remember, we're trying to work out what makes materials strong. So we're going to try and do a test now. And I need a volunteer to help me work out what are strong materials. Okay, brilliant. Let's take you over there. Fantastic. Yeah. Great. Over here. So, what is your name?
Natasha.
Natasha. Okay, Natasha. Now, are you up to helping me work out which are strong materials that we need for building?
Yep.
Okay, fantastic. If you go around that corner there, I'll come around here. I'll join you. Okay. Now, what we're going to do is we've got here a dresser like you might sort of have at home with some objects on it, and we're going to try and test them to destruction.
Okay.
And to get you in the right mood for this, I want you to think about the most furious moment in your life and how you felt. And in that moment you thought, gosh, I really want to throw this ball at that,
okay.
Didn't you? And okay. I'm also going to get you to put some safety goggles on. Is that all right? Mm-hmm. And so you're holding that thought, furious, and of course you could never do this at home. You would never do this at home. What? But here you can do it. Is this going to be the happiest moment of your life?
Yes.
Okay. Now, it's going to be a competition, which is always the way with me. So you're going to get 3 balls, I'm going to hand to you, and I'm going to get 3 balls, and we're going to see who can smash the most.
Okay.
Does that sound fair? I'm thinking furious thoughts, you're thinking furious thoughts, and let's see which materials can survive.
Okay.
Off you go first. Okay, wow. All right, now I'm going to do the same. Oh, not too bad. Funny. Off you go. Oh, sorry. Wow, you are quite angry inside. Okay. Whoa. All right, last go. Fantastic. Okay. I'm actually quite nervous now. Now, what's the score, everybody? Did you get this? It's 1 each. So I think there's a fair fury divide between us. Thank you very much indeed. Okay, so look. Let's just look at the wreckage in here. So this got hit, but actually this is paper and survived. That's all right, isn't it? And this metal plate got a bit dented, but survived. So they seem good candidates for strong materials. This cup bit the dust big time. Porcelain cup, clearly a weak material. Wouldn't you agree? Well, you would you? You've fallen into my trap. All right, is it weak? Let's see. We've got a replica cup here. Now, I want to show you how thin this is, because you know how thin they are, but I'm just going to show you. You can actually, porcelain cups are fine bone channel like this, you can actually shine lights through. Look at that. It's that thin. We're saying this is weak, but is it? I'm going to now do something which you shouldn't do at home. In fact, you shouldn't do any of this at home. Will you promise? Okay, but I'm going to stand on this cup and see if it really is so weak. I'm pretty hefty. I didn't get on those scales earlier because I was a bit embarrassed. But you see, I've got a lot of weight. Gravity's pulling me down. All of my weight's going on the cup. No problem at all. So, it seemed quite strong there, didn't it? Now, I know what you're thinking. You're thinking, they've got a dummy cup, this is a super strong cup, and that was a weak cup. So just to prove to you that's not the case, and because I can. So the cup was pretty strong when I stood on it, but is it going to be able to survive this? No. So what's clear from any tantrum you've ever had, and this test here, is that there are different kinds of strengths of materials, and that you've got a strength here which is about impact strength, and some things are great under impact, and they're terrible under other things. So paper was good under impact, but if I put a paper cup down here, it would crush. On the other hand, the ceramic cup was terrible under impact, and is fantastic under these compressive forces of me. So when we think about building buildings out of materials, what we really need to think about is which type of strength we want. And in the case of a building, we want more like the compressive strength. And so we have to make sure that we're picking materials with high compressive strengths. What do I mean by ceramics and that kind of thing? Well, a ceramic is a tiny, we saw it's a porcelain cup, and it's a tiny little crystals inside there. They're the same sort of crystals in jewellery. They're like rubies and sapphires and all these kind of aluminum oxides, silicon oxides, and they're tiny little crystals all munched together. And cups seem like a really good material to build a building out of. So you're thinking, why don't we have enormous buildings made out of cups? Well, we do. Because ceramics, that material, that class of material, is the same material as bricks. And it's the same material as stones and rocks and all these kind of materials. But I want to show you an even better material. And this is it! Concrete! Absolutely fantastic material! This is such an amazing material, and we all just take it for granted. I think because it looks so sort of grey and dull. And so we think it must be grey and dull if it looks grey and dull, but it isn't. It's the stuff of absolute phantasmo. Is that a word? Anyway, I've said it. Look, inside here is cement and gravel, and we're going to. If you set this, you can pour it. You can shift it up 200 meters in the air, pump it up through huge pumps. That's how they make really tall buildings. They pump it up. So it behaves like a liquid, even though it's sort of a gravel aggregate, and then when it gets there, it'll set. So it's not, as you might think, drying out. It's actually a chemical reaction is happening inside. Let me show you. This is what's happening. Little crystals are growing inside the concrete. So this is a ceramic, and it's incredibly good compressive strength. And what happens is that you've got this basically a liquid rock which you can pump anywhere, you can pour anywhere, you can bring on, and then you can make these enormous buildings. And then when they set, they have a huge compressive strength. So this is a fantastic material, and in fact, it seems that we've kind of come to the material we need to make big buildings that build us off the planet. We need rock, basically, ceramic. It could be concrete or it can be stone. But this is the way, surely, this is the way to build huge buildings. Well, it's no news. You know it. We've been doing it for 5,000 years. Let me show you. It's getting a bit hot here. Okay, yes. It's good to get some winter sun, don't you think? Look, I'm by the pyramids in Egypt. And this, these buildings have been built out of stone. And, they really show exactly what I'm talking about. They've lasted for 5,000 years. There's enormous compressive stresses at the bottom. And they've been there for 5,000 years. And this rock has not given up. Incredible down here. And so, surely, this is the right both material and structure to start building ourselves off the planet. So let's think about this. If I get a map out of central London here, and this is to scale, then we are, that's a very strange material. Anyway, sorry. We are here, Albemarle Street. This is the RI to scale. And it's got a little hole in the roof, just like this one's got a little hole in the roof. Okay, so let's try and build the tallest building in the world, but out of concrete, and let's do it in a pyramid structure. Because, where are we going to put it? I mean, there seems to be a lot of space here. There's Green Park, there's St James's Park, and there's this thing called Buckingham Palace Gardens. That seems to be unoccupied. That's amazing, isn't it? So that seems like a very likely spot. Yeah, let's do it. Let's have a go at this. So that we have to we have to ask the Queen. That's the first thing we have to do. I think she might be upset at losing her palace. She's got a few palaces, but she's pretty much attached to this one, I'm pretty sure. So we have to offer her space in this new building. That's what I'm thinking. And of course, we seem to have wiped out half of Mayfair here, and Belgravia and that kind of thing. So I guess that is the problem, isn't it? Is that pyramids are great, they last for a long time, they can cope with the stress. So that's all fantastic. We've got our structural head right on. Basically, this is the scale now. So if this would now be the tallest building in the world, in a pyramid, in the middle of London, which would be fantastic. It would be very impressive. But now, if you think about it, now if you try to build it even higher, let's say twice as high, so we're up there now, think how big the footprint would have to be. It would actually have to take over the whole of central London. And at today's house prices, that would just be a mammoth planning task, wouldn't it? And then that would only get you so far, and even then, how high would we really get? So that's a real problem with pyramids, is the plan area at the bottom that it takes up. But there's another problem with pyramids. If you think about it, mountains, like this is a picture of Mount Everest up here, mountains are essentially pyramids, aren't they? They're peaked at the top and have a wide base. And turns out, so we can study them, and that actually Mount Everest is at 10 times bigger than this pyramid here, if this was the highest building in the world, 0.8 kilometres. That's about 8 kilometres high. Basically, nature builds mountains itself, so builds pyramids, and they don't get bigger and bigger and bigger. Actually, they sort of stay rather small. Now, why is that? Let's have a look at that, because that's odd. You would have thought the geological processes in the Earth would allow us to get much bigger mountains than that. But here's the problem. This pyramid and that mountain are heavy. They're big objects. That mountain is 2 or 3 trillion tons. So when it sits on the Earth's crust, and this, in case you were about to ask, and I'm sure you were, is a model of the Earth's crust, and then underneath the mantle, right, it's hot. So So we've got the crust and the mantle here, and it's hot rock. It's solid rock, but it's hot. Now, over millions of years, 1 trillion tons of mountain sits on that hot rock, and this is what happens. It starts to sink. Why? Why does solid rock behave like a liquid and let things sink in it? That doesn't seem right. But it turns out that over millions of years, if it's hot enough, and it is hot enough, it flows like a liquid. And so the process of mountain building on this planet is things pushing stuff up, geological process, making mountains, and then sinking back in. And the balance of those two forces determines the height of the mountains on this planet. Now you think, well, hold on a minute, surely you could just get some enormous eruptions and get much bigger mountains like this one, which is 3 times the size of Everest. I mean, not really 3 times, but 3 times the size of my model of Everest. And so let's see, what would happen then is that, well, it's much more than 3 times the weight, as you'll know if you listen to lecture 1. And look at that. It's sinking down and down. So you've got much more mass being pulled down by gravity. And it keeps going down, and it keeps going down, because actually the buoyancy forces, which are opposing these gravitational forces, mean that this has to sit much further down than you expect. And this will keep going down. So you can't just keep building bigger mountains and hope for them to stay around, because the rock just behaves like a liquid and they sink. Now you think, well, okay, why can't we do it on another planet which has a lower gravitational field, right, strength? So like Mars. Good question. And there it is. Olympus Mons on Mars is 3 times taller than Everest. So it is bigger on Mars, but it does have a lower gravitational field. So clearly that this balance of forces is correct. But it's still just a pimple on the surface of Mars. So we can't build our way off the planet by building with big, heavy stuff. We need a material that's strong and light. So we need something that has a high strength-to-weight ratio. So let's think this through. I'm going to need a volunteer to help me on this one. Yes. Who have I? Yes, you, sir, on the end. That's yes. Okay. Hello. What's your name? William. Okay, William. All right, now I've got something to show you here. So we're talking about, we want something strong and light. Okay? I've got 2 materials here, and they're both strong. But we want to kind of work out which one's stronger and lighter, so it's a bit of a calculation. Steel bar, there we go. Now, I want you to try and break it. Just bend it until it can't bend anymore. Oh, well, that's cheating, but fair enough. Okay. But it's pretty strong, isn't it? No chance, right? Now, what about this? This is another material that's very strong. It's called a carbon fibre composite. Try and bend that. What? Yeah, it's different, isn't it?
Yeah.
Now, which one of them has the best strength-to-weight ratio?
I assume it would be this one.
Ooh, I like it. But how could you tell? Because actually it doesn't seem like a fair test, because did they weigh the same?
Not really.
No, and you, in order to work that out, you'd have to work out how much you were tensing it. So what you'd like to see, wouldn't you, is the same weight objects. So a piece of steel the same weight as that. That would be much easier. Good thinking. All right, so let's get something the same weight, and let's weigh it just in case people think it's not the same weight. So here's the steel. So that's 145 grams. All right. Now try and bend that. Yeah, go. You could just, you can make noises as well if you want. I do. All right. Now, if this one's worth 145 grams or thereabouts, we'll then try and test that one again, shall we? So this one is 145 grams. Same weight. Now bend this one. No chance. So suddenly, your original assumption about this one being the best for strength per weight is absolutely correct. Yeah. Genius. Thank you very much. So, composite materials, these carbon composites are really amazing. They're strong but light. And these are revolutionizing people's lives. Have a look at this.
And it's another golden route to the line for British cycling. The latest star is Jody Cundy.
Jody Cundy, come on! Here he comes. Jody, tell us about your credentials.
Well, I'm a double world champion, multiple world record holder, and double Paralympic champion in track cycling. And that was me winning in the kilo in Beijing.
And how much of it is you, and how much of it is this marvellous material that your bike is made out of?
Well, I like to think a lot of it is me making the bike go fast, but the carbon fibre we have in the bikes really helps us go fast. I mean, they're shaped aerodynamically, so we cut through the air. I mean, even my leg is made of carbon fibre to cut through the air.
Wow.
The frame's made of carbon, the wheels are made of carbon, the handlebars are made of carbon, and the seat post. So pretty much everything on this bike is carbon. It's basically there, so we transfer all the power that we've got in our legs and make this back wheel go, so we go forward.
That's incredible, isn't it? So your leg is actually the cycling legs. So
that's right. Yeah, it's completely useless for walking in, but it's got a cycling cleat on the bottom, just like any other shoe, and it clips into my pedals.
That's amazing, isn't it? Can I just see how light
sure,
it is?
yeah.
I just want to see if I can lift it up with one finger. Oh yeah. This is a thing of beauty, isn't it? An absolute thing of beauty. Well, thank you so much for coming. No, a real privilege to meet you. Thank you. So it's not just in Olympic sports and in incredible extreme sports, but it's also in your everyday life. This is a material that's really going to be affecting every one of you. I want to show you the latest aircraft from Airbus. This is the A380. This is a double-decker plane. 20% of this is carbon fibre composite. And this is only going to increase. As the years go on, I'm pretty much confident that in 10 years' time, 70 or 80% of aircraft will be carbon fibre composite or other composites. And in fact, we brought some in from an actual A380 here. So this is part of the underwing components. We've got two bits of it here. It's carbon fibres, so a bit like the graphite in pencils, but made into a fibre. And then it's interwoven. You see it here. Actually, it's interwoven with a resin, so a plastic. So that's why it's called a composite. It's part fibre, carbon fibre, and part resin. And this resin, this plastic, is sort of also, sort of thing you get with araldite. I mean, not so almost like a glue. But either of them on their own is not so useful. You put them together and you get this marvellously strong material. I want to just sort of give you an experience of how strong these materials are, and I need a volunteer. Yes, what about you on the end with the Christmas hat? What's your name? Katie. Katie, are you strong, Katie?
Yeah.
Okay. Have you got a bad back?
No.
Good. Okay, I just want you to just lift this up, and then I'll tell you what to do later, okay? Do you think you'll be able to lift that up?
Yeah.
Oh! It's actually quite light, isn't it?
Yeah.
Oh, okay. Well, you could look a little bit more surprised if you like. No, don't worry. Isn't that amazing how light that is? Are you surprised?
Yeah.
It's incredible, isn't it? I mean, that's just an enormous piece of stuff, isn't it? And it's very light. In fact, it's so light, you continue to hold it. Are you getting strained? No, it's so light. Watch this. I can lift this up with one hand. It's the size of a wardrobe. And yet, all right, come on, guys. Okay. Thank you very much. That was actually, I wasn't going to get you to smash it because there's been enough smashing, hasn't there?
Yeah.
Thank you very much. So the key to this material is its strength to weight ratio. It's really fantastic material for that. So could we use these materials to build ourselves off the planet? That is the question. And make things that are really, really tall. and really let's defeat gravity once and for all with these light materials. Earlier here, we were looking at the Earth, and we worked out that we had to get 36,000 kilometers over here before we could really get out of the grips of gravity. So what we want to try and do is build a building 36,000 kilometers high. And we already worked out that we need something with very high strength to weight ratio. So let's see how all the materials that we've so far come across do on that rating. Oh, are you still got your common sense turned on? That is a very silly material. All right, now this is a sort of scale model of the Burj Khalifa. So this is the tallest building in the world, scaled down. So it's 0.8 kilometers high, so half a mile high. Now, if we were to build a building out of steel, right, so pure steel, solid steel, and just keep going up, 100 meters at the bottom, and just keep going up, we'd get up to 4 kilometers high. So we could, at the moment, build a building 4 kilometers high, no problem at all. If we use concrete, we'd get up to 4.7 kilometers high. That's incredible, 4.7, I mean, it's just insane, isn't it? And it really makes the current buildings that we're living in look just puny. And actually, you probably know this, but actually modern buildings are often built with a combination of steel and concrete. So if you do the calculations, you could probably get up to 5 kilometers with a combination of these two materials. So 5 kilometers high for these materials that we kind of know about. What about carbon fiber? What about this fantastic material with strength to weight ratio that's much better? Well, let's see. It's actually extremely high. It's really impressively high. We actually have to go higher and higher, higher than the steel, higher than the concrete, higher than a combination of steel and concrete, and even higher and higher and higher to 7 kilometers. So we could build a building 7 kilometers high with carbon fiber composite. A material that's really light but strong, and the advantage of that is that there isn't this huge mass bearing down on it because it's so light, and yes, it's really strong, so it can really withstand the loss of its own weight. And the other brilliant thing is the view is fantastic up here, absolutely amazing. 7 kilometers is really impressive. And let's say we could really make some advances. We could get to maybe 10 kilometers if we increased better the design. Maybe we could get to 100 kilometers in the next century or so. It still wouldn't be anywhere near 36,000 kilometers, which we'd need to build ourselves off the planet. And that's what we want to do, right? That seems like a really great thing to do. And yet, So is there another way to think about this problem? Crikey. Well, but yeah, you're right. I mean, I can see your point that you're trying to make with that. Because spiders, they don't build up. They've got more sense than that. They build down. They go up to the top, and then they come down on a little fibre. So that gives me an idea. Why can't we do the same thing with this problem? Let's just turn the whole thing upside down. And let's not build up. Let's build down. Or not build, let's send a cable down. So if I'm here orbiting the Earth as a satellite, okay, and then I get a cable and I send it down to Earth like this, and I keep sending it down, and I keep going, and I keep going, and I keep going, and I keep going, and I keep going for 36,000 kilometers. And then, when we get to the bottom, what we do is we tie it off. I know that sounds ridiculous, but yeah, just go with me on this one. We tie it off, and now we've got a cable from a satellite orbiting the Earth to the Earth's surface. Now, attach an elevator to that, and what do you have? But you have a space elevator. And we could just get into it and go up to space. How fantastic would that be? That would just be brilliant. Now, the thing is, of course, when you're paying a cable down, there's huge gravitational forces pulling it to Earth because there's an enormous weight of this cable. So again, you need something with very high strength to weight ratio, wouldn't you? So how strong does it have to be? And if you do the calculations, it turns out that you need something that would be as strong that if you had a 1 millimeter thick fibre of it, so not something a bit like a thread, it would have to suspend the whole audience, which is 20 tons. So that seems like quite a big task. Well, I've been thinking about this, and we do have fibres that are very strong, don't we? As a scientist, it's a very competitive field. And often I get the feeling that people want to take a bit of a pop shot at me. So like a lot of other scientists worried about this, I have a body double. And occasionally I send the body double to conferences instead of me just to see what happens. And the other week, this is what happened. I knew it. I knew they were after me. But luckily, they mistook my body double for me. And here he is. He survived. Now, the reason he survived, and it's not really him because he's obviously plastic. I know that. But he's got one of my shirts on. And I didn't want him to get hurt. So I put on a Kevlar bulletproof vest. And you can see that the bullets, they went in here, we've just taken that bit off there, and in through here. But they didn't make it through the Kevlar. So these bits on the outside, these are sort of nylon, sort of just outer layers. Inside there is the Kevlar. Now Kevlar is an extremely strong fibre. I'm going to show you where the Kevlar is. It's in here. That's Kevlar. It's an extremely fine weave and extremely strong fibre. So what is Kevlar? It's a set of molecules that have been assembled molecule by molecule at the atomic scale. And so its strength really is very close to the atomic strength of those molecules together. And so you're breaking atomic bonds to break this material, and that means that it's extremely strong. Is it strong enough, though, to build the cable for the space elevator? And it turns out to be not. Right? It would only support a couple of people, a thickness of that fibre. So although Kevlar is fantastic for saving lives, and it really is the material of choice, it isn't good enough for what we want it to do. That's a bit of a problem. But recently, there's been some material science discoveries that have kind of given us hope. And it turns out that the ingredients for this material that's given us hope, you've experienced yourself at every birthday you've ever had. And I just want to ask, is there anyone here whose birthday is this week? It's your birthday this week? All right, would you mind coming down? Hello, what's your name? Catherine, and it's your birthday this week, is it? What do you have on your birthday? A cake! Fantastic, here we go. Birthday cake for you for next Monday. Now, would you believe that the ingredients for a great new material are here? Where are they, though? Are they in the cake, the icing, the ribbon, the wax? Well, let me just take a sample of it. And now you can blow out the candles if you like. Happy birthday! So on this glass slide, I collected some of the ingredients for this material. And it turns out that until 10 or 20 years ago, we thought that there were only two forms of carbon. There was diamond, which is super hard and translucent, and there was graphite, which you use in pencils, and we thought that was it. And then people started looking around and realized that actually carbon could arrange itself in some other amazing ways. And one of them we found in the soot of candles, which is an incredible place to find it. So here, in here, are molecules that look like this. And they're called buckyballs. And they're a different way of arranging carbon. And they're really beautiful things. And if you use these and you recombine them, you can make things like this. And these are called carbon nanotubes. And this is a fantastically strong and light material. The reason is this. It's mostly carbon. Well, it's only carbon, isn't it? It's carbon. Now, carbon's a really light element. It's one of the lightest elements of the periodic table. So your ingredients are really light. The bonds between them are really strong. This is a really strong structure here. And then in the middle, there's nothing. So there's even less density, right? So these things are... You all know what it's like when you have a piece of paper and it waves about. And then you wrap it into a column, and suddenly it's strong and stiff. You've got the same thing going on here. So at a molecular level, this thing is an extraordinarily strong structure. In fact, it is theoretically, like when you do the calculations, you do the quantum mechanics calculations, you find that this has the strength we need to make a space elevator cable. But of course, they're tiny things. Let me show you how small they are. Well, I can't really show you how small they are, because all I can show you is a jar of them, and they're individual little nanoscales. I mean, this is at the scale of 1 billionth. So they're a billion times smaller than this. So the big challenge is then to join these up into one long thread. And that's really difficult. Then to get those threads into a twine and then into a cable, right? So if you're familiar with suspension bridges, you've got small bits of steel into a twine, bigger bits of steel, bigger, all wrapped around. So that's a cable. So let me tell you how far material scientists have got. They can make nanotubes. So they can do that. And here is some of the first ever in the world examples of threads made with nanotubes. And this really is an amazing sample. This is made in the Windle lab in Cambridge, and it really is the idea. It is these joined together in a thread. Now let me show you under the microscope. This is an incredibly exciting moment for everyone, because we've been all hoping that this material could be made. And this is really the jump between theory, so the theoretical material science, to the practical material science, and then to the engineering. At the moment, it's not there yet, but it's going to happen. People are going to get better and better at making this into that material. And when they do, we're going to have a material that can make a space elevator. If we've got the materials that we can make this cable out of, and that was the big challenge, the rest looks pretty straightforward. Let me just talk you through what we'd have to do. We'd have to get up into space, and we'd have to get a satellite that was orbiting the Earth, geostationary orbit, 36,000 kilometers. Then we have to work out a way of making the material up here, because we wouldn't want to get up here all the time. So we make it up here, and we start paying out this cable down. 36,000 kilometers down. Then we tether it to the Earth. Now that, you can see where it hits is in the ocean. We want it on the equator, and we want it in the ocean because we want to tether it to a boat. So if there's any movement, it is taken up by the sort of viscosity of the sea. Then how would you, and of course you're all thinking this, but hold on a minute, all that would just collapse under its own gravitational weight back into the Earth. Good thought. And so what we'd have to do is we'd have to kind of have a counterweight. So we'd send out a piece of material this side, which exactly has the counterweight of the force going in. So the whole thing's in balance. Now what happens is that you decide you want to go to space. Any of you. And so you get a boat to the docking station, and you get on the elevator, and you come up 36,000 kilometers, and you hit, and suddenly you are weightless. How fantastic would that be? Our parents' generation, they went to the moon. They gave that as a present to us, and it was an incredible achievement. And we've got to live up to that. We've got to do something just as good. We've got to give something to the next generation. And this, I think, is it. This is our challenge for our generation. This is what's left over for us to do, to make mass space transport via an elevator possible for everybody. So let's do it. Come on, guys, let's just do it. Don't you think? hope you've enjoyed these lectures about scale and materials. And we've seen that if everything changes as you get smaller. Things get super strong. You can survive enormous falls. You can engineer materials to be incredible. You can devise invisibility shields. And ants are super strong when they're small, and hamsters are super strong because they're small, and they can survive these enormous falls just because of their size. But we get to live longer than them because we're large. So it all depends on how big you are. Size really does matter. And I hope that you've enjoyed this tour through the scale of the universe and life. Thank you very much for listening.
The BBC and the Royal Institute are producing a free pack for secondary schools to accompany the lectures. For details, go to bbc.co.uk/teachers. Stay with us here on BBC4 Next. We're defying gravity and heading to the moon, thanks to a dose of Cavorite and H.G. Wells.